Hey everybody, thanks for joining our presentation. Today we will be presenting our UVSim project. It is a virtual machine simulator designed to execute machine language programs through a graphical interface. Our application allows users to load program files, edit them directly within the interface, and execute instructions, either step by step or all at once. That flexibility makes it useful for both detailed debugging and for running complete programs. In our presentation, we'll walk through the system's architecture, discuss some key features, showcase the application, and conclude with potential future improvements. UVSim is designed to simulate a simplified computer system that executes low-level instructions. The purpose of this project is to give users a way to understand how machine-level programs operate internally, including memory handling, instruction execution, and control flow. This provides a clear visual representation of these internal processes, assisting with practical learning. We focused on building a modular and maintainable system that separates our UI, or the user interface, from the core logic and the execution engine. This design choice improves our code's readability, makes testing easier, and allows for future developments to be made without rewriting the core components. Our system consists of four main components. The first is the GUI, which handles all of our user interactions. This includes displaying memory and register contents, responding to the button presses, and showing program output to the user. The second is the simulation engine that manages memory, program loading, and the execution flow. This component acts as the central coordinator, keeping track of the program's counter and ensures that all instructions are fetched and executed in the correct order. The third component is our operations, which contains the logic for executing individual instructions. Each of the instruction types have their own dedicated function, making the code organized and easy to modify if new instructions are needed to be added later. Our fourth component is our configuration manager, which manages user-defined configuration settings, such as theme customization. This allows the users to adjust the appearance of the application according to their preferences without affecting the core simulation logic. An example is the color. This separation ensures a clean architecture with loose coupling between components. For example, changes to the GUI don't require changes to the execution engine and vice versa. This makes our system more robust and easier to maintain over time.
Our application includes several key features. Users can load and save program files from any directory on their system. When a file is loaded, the application automatically validates every line to make sure it follows the correct format before displaying it in the editor. The interface supports multiple files open at once using a tabbed layout, allowing users to work in several programs simultaneously. Each tab maintains its own independent simulator state, meaning you can run or step through one program without affecting any of the others. Users can edit instructions directly in the GUI, including copy, paste, insert, and deleting operations. The editor also validates input in real time, catching formatting errors like missing signs or incorrect digit counts before the program even runs. We also support both step-by-step execution and full program execution, giving users flexibility in how they run programs. In step mode, the memory panel, accumulator, program counter, and state all update after every single instruction, so users can watch exactly what the simulator is doing at each point. If a program requires user input, a dialog box appears automatically asking for a value, and that value is validated to make sure it falls within the allowed range before being written to memory. Additionally, the interface supports customizable themes based on user configuration. Users can open a color picker to change the background color of the application, and that choice is saved automatically so it persists the next time the program is opened. UVSim supports two file formats, the legacy 4-digit format and the newer 6-digit format. The 4-digit format uses 2-digit operation code followed by a 2-digit memory address, while the newer 6-digit format expands this to 3-digit operation code and a 3-digit memory address, allowing the system to reference a much larger address space. Each instruction must begin with either a plus or a minus sign followed by the instruction code. This sign indicates whether the value is positive or negative, which is important not just for the instruction, but also for the data value stored in the memory. The system supports a maximum of 250 locations, numbered from 0 to 249. This is an expansion from the original 100 location limit, giving programs significantly more room to store instructions and data. Any instruction that references an address outside of this range is automatically rejected with a clear error message. We enforce strict validation rules to ensure that the files do not exceed these limits and that formats are not mixed within a single file. When a file is loaded, the system automatically detects whether it is in the old or new format based on the length of the first valid instruction. If an old format file is detected, the instructions are converted internally to the 6-digit format so that the simulator can handle both seamlessly without requiring the user to do anything manually. The execution model follows a fetch, decode, execute cycle. The simulator reads an instruction from the memory, figures out what it means, and carries it out before moving on to the next one. The simulator decodes each instruction by splitting it into opcode and an operand. The opcode tells the simulator what to do, and the operand tells it which memory address to work with. Supported operations include arithmetic like addition, subtraction, multiplication, and division, as well as input, output, and branching instructions. Branching allows programs to jump to different memory addresses based on conditions such as whether the accumulator is negative or 0, which is what makes loops and decisions possible. The accumulator holds the result of arithmetic operations and is used for load and store instructions. The program counter tracks which instruction runs next, advancing automatically after each step, or jumping to a target address when a branch instruction is executed.
Users interact with the system through the graphical interface. This makes the simulator much easier to use than a command line only workflow, because the user can stay inside one environment while loading, editing, and testing programs. It also makes the project more approachable for first-time users, since they can see the state of the simulator visually instead of having to interpret everything through raw terminal output. They can load a program into a tab, modify instructions directly, and execute the program using either the start or step functionality. Input operations such as read prompt the user through dialog boxes, while output is displayed within the interface. The tab design allows users to switch between multiple open files easily. The ability to move between multiple open files is especially useful during testing and debugging, because users can compare different programs or keep earlier versions open while making revisions. Our application includes comprehensive error handling. We validate file formats to ensure proper syntax, including enforcing the requirement that each instruction begins with a plus or minus sign. We also handle runtime errors, such as invalid opcodes, invalid memory addresses, division by 0, and arithmetic overflow. When an error occurs, the system displays clear messages to guide the user. This is important because a simulator like this needs to be strict enough to catch mistakes, but also clear enough for the user to learn from them. The system checks for problems before execution whenever possible, which helps prevent invalid files from moving deeper into the application and causing more confusing errors later. That means error handling is not just a technical safeguard, but also a teaching tool, because users receive direct feedback about what went wrong and where to look to correct it. The application includes a configurable theme system. By default, it uses UVU branding colors. Users can customize the primary and secondary colors through a configuration file without needing to recompile the application. These settings can be applied when the application starts, allowing flexibility and personalization of the user interface. Although theming is not part of the core machine execution logic, it improves the overall polish and usability of the project. It shows that the system was designed not just to function correctly, but also to present itself in a professional and user-friendly way. Allowing theme customization without recompiling also makes the application easier to maintain and adapt in the future. This is a small feature on the surface, but it reflects a broader design goal of building software that is both functional and practical for real users. Looking ahead, There are several potential improvements for this application. These include developing a web-based version for broader accessibility, adding debugging tools such as breakpoints, and implementing a visual memory inspector. Additional enhancements could include collaboration features and a mobile version of the application. One of the most valuable future improvements would be a web-based version, because it would make the simulator more accessible without requiring local setup or installation. Expanded debugging features, such as breakpoints, would also make the system more powerful as an educational tool by giving users more control over how they inspect execution. A visual memory inspector could improve clarity by helping users see how memory changes over time in a more intuitive way. Together, these future enhancements show that the project is not only complete for its current goals, but also structured in a way that could support continued development later on. In conclusion, UVSim successfully meets the requirements of a modular virtual machine simulator. It supports file loading, editing, execution, theming, and multi-file management. What makes this project especially valuable is that it does not just meet the technical requirements on paper, but presents them in a way that is practical and understandable for the user. It takes the core ideas of machine-level execution and makes them easier to observe through a clear interface, visible memory state, and guided interaction. The system is designed with scalability and maintainability in mind. As the project developed, it grew from a simpler prototype into a more complete application, which reflects both the technical work behind it and the design decisions that helped shape the final result. So overall, UVSim represents not only a working simulator, but also a system that was built with long-term improvement, usability, and future expansion in mind. Thank you for your time, and we're happy to answer any questions.